Hello, my name is Nick Mowry, and in this video I'll be covering the scalable coordination architectures for deeply distributed systems, distinguished here as SCADDS Diffusion version 3. This paper, titled Building Efficient Wireless Sensor Networks with Low-Level Naming, was published in 2001. The research was conducted by USC and UCLA with funding from DARPA and support from Cisco Systems. In the beginning, we had flooding. Flooding is a fairly rudimentary process for broadcasting data in such a way that a source sends data to the entire network with the intent of delivering it to one or more sync nodes. Gossiping takes the same approach, but only sends the data to some of its neighbors, resulting in a lower energy consumption, but is also slower and less reliable due to a reduction in successful delivery percentage. In the late 90s and early aughts, this was advantageous because inherent hardware constraints meant memory and processing were at a premium. To put this into perspective, the roughly 5 kilobytes required to code this type of network architecture was more than half of the available storage for the more cutting-edge platforms such as the MIT motes, as described in class. Its methods are kept simple by each node being unencumbered by any topological maintenance of the larger network. Even if we consider more powerful hardware solutions available today, the benefits of this simplicity are far outweighed by data and energy losses across the network. At the core of the inherent inefficiency are implosions, overlaps, and a general resource blindness. As we know, flooded networks lose data in events called implosions. When an event is registered by a sensor, it begins flooding the network. Implosions occur when a sensor receives multiple packets simultaneously. Similarly, flooding cannot account for multiple data packets being sent in response to a single event. Both of these occurrences lead to wasted hops and therefore reduce the longevity of the entire network. As with many other approaches, SCADDS seeks to reduce this inefficiency by using algorithmic restriction of data migration within the network. The authors of this paper developed their approach by augmenting standard directed diffusion with additional functionality. In standard directed diffusion, interests are injected into a sync node within the network, seeking out specific sensor activity. Interests are comprised of attribute value tuples. It first floods the network to determine gradients between its neighbors recursively until a sensor node is found which has detected an event. These gradients can be based on one or many factors, which might include latency or energy state. Once the gradients have been determined, the path is reinforced as determined by the gradients, and the data is sent back along this path. Each hop along the path adds the interest to the local node's caches, and at lower levels, this can mitigate data duplication by merging data into a single response. Periodically, the sync will rebroadcast the interest. If the network experiences interference or if a sensor node is becoming energy depleted, the gradients can be negatively reinforced, thereby dynamically changing the path. This negative reinforcement also suppresses loops and duplicate data. Now, where the SCADDS approach starts to deviate from simple directed diffusion is in how tuples are defined and in the use of matching rules. In this approach, attribute tuples consist of an attribute, an operation, and some value. Attributes may be related to the class of the packet to distinguish between data being carried, intent messages, and, as we'll see later, filters. Attributes data formats are defined implicitly as integers and floating point values of different sizes, strings, and uninterpreted binary data. It can use each tuple's binary operator to express data stored almost like variables. It can also use the same set of operators to compare cached messages in a node with data it receives at a later time. Each message contains at least one or more tuples which provides its own class definition. This allows it to define interests as expected from a system built on directed diffusion, but goes further by adding rules to the types of interests a node will reply to. There's a non-trivial distinction to be made between the formal operators on the left side of the screen with the actual operators on the right. Formal operators function as one would expect with Boolean operators acting on two values. However, the actual type operator is, shown on the right, is used as a literal or bound value. By making this distinction, a one-way match compares all formal parameters of one attribute set against the actuals of the other. Any formal parameter that is missing a matching actual in the other attribute set causes the one-way match to fail. Similarly to the way interest messages are handled in directed diffusion, these matching rules are executed as a node receives a packet and compares them against its internally cached tables. Here, the key is a unique identifier for sensor attributes assigned externally to the network. Two sets of attributes have a complete match if one-way matches succeed in both directions. In this example, we have an interest injected into the network for a four-legged animal in a specific region for the next 10 seconds. Take note that the actual operators for type and regions use formal operators. Take note that the operators for type and regions are formal operators. Also, we see that the author's clever use of the implicit data type thereby reduce the packet sizes for these common messages. Put another way, when these messages are sent, if no class is defined, it's implicitly defined as a class. These formal operators are compared against the actual values here for type and specific sensor location. Now let's say sensors in the network are programmed with animal search routines. We can say that these comparisons are all ANDed since all formals must be satisfied to produce a successful match. In this example, when the sensor event matches a received interest, a message like the one shown here is sent back to the interested node. As we can see, the message can be supplemented with additional data the sensor may have. In this example, the sensor added intensity, confidence, and a timestamp. Another advantage of using this matching scheme over standard directed diffusion is the ability to push data as well as pull it. To do this, sensor nodes can watch for interests, in this case, four-legged animals, by expressing interests in interests. So the data type that would be sent, the message type, would be of class interest. Filters register what kinds of data they can handle through matching. They are then triggered each time that kind of data enters the node. When invoked, a filter can arbitrarily manipulate the message, cache data, influence how or where it's sent onward, or generate new messages in response. Filters have access to internal information about diffusion, including gradients and lists of neighbor nodes. In practice, filters are typically used for in-network aggregation, collaborative signal processing, caching, and similar tasks that benefit from control over data movement. In addition to these applications, the authors used them for network debugging and monitoring, which I found quite clever. To continue the previous example, a filter could be implemented on each sensor node to suppress concurrent detections of our four-legged animal searches. Using the specified interval, it could then limit the replies accordingly. With additional attribute operation value tuples, it could also suppress replies from neighbors or even count the neighbors to sense the same count the neighbors which sense the same event and add this as another attribute tuple. Taking this a step further, a confidence level could be generated based on predefined algorithms. As with other sensor network implementations, this in-network processing would result in a loss of fidelity, but increase overall network lifespan. Again, class is inherent. As implemented by the authors, filters can be leveraged to inject code into the network. This then allows for nested queries where sensor nodes modify their own data with data from neighbors. With further filtering, data suppression and aggregation greatly decreases the ratio of sent data to counted events. The data described in the graph here shows the suppressed and non-suppressed data usage. In tandem with its in-network processing capabilities, the SCADDS form of data-centric networking is a powerful yet efficient and versatile yet elegant approach to sensor networks. Thank you for your time.